This slidecast will cover standard library algorithms and function objects. To find an integer in a list, we could use this find function. It takes a list as a parameter and a target value. And then using iterators, we start at the beginning of the list and we iterate through each element. And when we find the target, we simply return ITR, which will be an iterator that points to the target. If we don't find it, then we return an iterator that points one past the end of the list. Now, if we wanted to find a string instead of an int, then we could rewrite the function. But rather than writing different copies of the function to work with the different types, we will use template functions. And they're like template classes in that we can define a template parameters that are replaced with the actual parameters at compile time. So just like we don't want to create, a separate class for every type of item that we can store in a collection, we don't want to create or replicate a function and have it a new function and change it just to handle a different type. So let's look at an example. Here's a find function. We start with this template type name item type. That's similar to when we defined template classes. And following this template specification, then we have our return type and the method name, followed by the two parameters, aList and target. Then we define an alias so that an iterator is equal to this type. And then we begin it at the beginning, and until we reach the end, we loop through this for loop, and we basically check if we find the target, then we return the iterator pointing to it. Otherwise, we return an iterator that points one past the end. Now, what if we wanted to search a vector instead of a list? And because the search loop is controlled by an iterator, the inventors of the STL chose to add an iterator to the container to be searched as a template parameter as well as the element data type. So the standard template library function find is effectively defined as follows. So we have a template, and in this case we have two sort of type parameters. We've got an iterator and an item type. And here we call a find function that takes a first and last iterators as parameters, and it returns an iterator. And then we say, and then the third parameter is the target, and it's a const reference. And then we can say, well, first is not equal to last if the value that first points to is equal to target, then we can return that iterator. Otherwise, we increment first. And then when we're finally done, we return first. Now in function find, the iterator parameter first points to the first element in the container and last points just past the last one. And the actual types of the iterators and the target are determined at compile time. So if list1 and vector1 are a list and a vector respectively, we could search these containers using the following function calls. So here's using lists, kind of begin and end. We can output, if we find a 10, then the list 1 contains a 10, otherwise list 1 doesn't contain a 10. And here's a find function for the vector to see if we can find ABC. And it either finds it or it doesn't. Now the actual types of the arguments to find don't have to be iterators defined by a container. An iterator is a generalization of a pointer, so pointers could be used as well. So we can call find by passing pointers to the beginning and the end of an array. And in the following if statement, the pointer list data points to the first element of the array, and then list data plus 7 points to the element just past the end of the array. So if this is our list data, here's where we invoke the find function. And the standard library contains several template functions defined in the header algorithm. And like find, many of them work on a pair of iterators that defines the sequence of input values, and some of them also take function objects as parameters. So here, this is taken from your book and shows functions and their behavior. you should pause and go study that on your own. Now, a template function performs fairly standard operations on containers. You could apply some function to each element, that's for each. We can copy, we can find, and we can sort. And most of these algorithms are simple loops, such as find, and you could ask yourself, why not just code the loop when we need it? And the two reasons: first, we avoid reinventing the wheel, because the library has validated versions of algorithms that have already been tested. If you recode it yourself, we could have errors that you'd have to fix rather than avoiding them in the first place. Now, the compiler can be designed to generate more efficient code when instantiating the library version of the algorithm than if you were to hand code the equivalent C++ code. So this fragment copies the contents of an A list to a vector. So we call resize on vector, and we pass it the size of the list. So this makes the vector be the same size as a list, and then we copy from the beginning to the end of the list, and we place it in, starting at a vector begin, which is an iterator that points. This is basically an iterator that points into the vector class where we will insert items. The first statement sets the size of the vector the same as the list, and then it calls a template function copy to copy the elements from the list to the vector. Here's a fragment that sorts the elements in a vector and then accumulates and displays the sum of the elements. I think look through each of these sections on your own and see if you have any questions you can bring to class. Now, the swap function is defined. It's a template function which takes x and y, which are references to instances of type T, and we copy x into the temper into temp. This is the copy constructor. We assign y to x, and then we can assign the copy of x to y. Now, we use the template function swap in 4.3 to exchange the contents of two variables. And here's some example in this standard swap, swapping num items or the current capacity or the data. The first two calls exchange a pair of ints. The last call exchanges the pointers to the two arrays. What if we have two vector variables and we have this statement, swap v1, v2? In this case, the copy constructor will be invoked to make a copy of v1 into temp. Then the assignment operator will assign v2 to v1. Then temp is assigned to v1 using the assignment operator again, and the destructor is called to destroy temp. Now, since the standard swap uses the assignment operator, which in turn uses the copy constructor and the swap member functions, we are making unnecessary copies. So we can avoid this by having a specialization of the swap. And in this function definition, the compiler will instantiate the vector swap member function rather than the standard function swap when it's called with the arguments of type vector. And this function definition is placed in vector.h after the class definition. Now, the function call operator can be overloaded, and a class that overlays this operator is called a function class, and an object of such a class is called a function object. So as an example, we may want to find a value divisible by another value, and we can create a function class divisible by whose constructor takes the divisor as an argument. So the data field divisor stores the number we want to divide by, and the definition of this operator specifies that the function result will be determined by testing the remainder resulting from the division of the function argument by the divisor. And the expression divisible by 3 creates a function object that returns true if the argument passed to it is divisible by 3. And the expression divisible by 5 creates a function object that tests for integers divisible by 5. So here's another function, its behavior. This finds the first occurrence of an item in the sequence, for which functions pred returns true. If it's not found, last is returned. So the template parameter II is a placeholder for an input iterator, and the template parameter P is a placeholder for a function class with an overloaded operator function that returns a Boolean value. Here's a template function find if it's instantiated with an iterator bound to the list int iterator. And this instantiation is called with two different function objects, but these objects have the same type. On the next slide, the function class squareDiff saves its argument in a data field mean. And the function call, redefining this operator, subtracts the value saved in mean from the input value and then returns the square of this difference. So here's our squareDiff class. Here's our constructor that just does an assignment initialization list and doesn't have any body. Then we subtract the mean from the input value and return the square of the difference. That's the meaning of this. And we can use function object squareDiff to compute the standard deviation of a collection of real numbers using the formula below for standard deviation. Now to get the mean, we first compute the sum of the data stored in the container and then divide by the number of values. So if we had to compute the sum of the input, we'll start out with the begin and end iterator calls to input data, and then we can compute the mean. And we can use a transform algorithm with a function class squareDiff to transform the values in input data into a sequence of squared deviations. So the following statement applies to the function call operator in function class squareDiff to each element of input data. So because the third parameter is an iterator that points to the first element in the input data, the result of each call is saved back in input data. So this code loads the square deviation values. So finally we use accumulate to compute the sum of the square deviations, and then the standard deviation is computed. So here we call accumulate. We get a beginning and ending iterator. This might be the beginning sum, which is 0. And to compute the standard deviation, once we have this sum sqdev, then we can take that value and divide it by the input data size minus 1. And if we take the square root of that, we have the standard deviation. And that's the end of this slidecast.